Hi, everyone. My name is Shreya. As Leon said, I'm a PhD student in mechanical engineering working with Jeff Grossman in the Department of Material Science and Engineering. This looks like a previous slide deck, but I'm excited to talk today about our work in membranes for water desalination. We're looking at new materials that change the inherent properties of membranes for reverse osmosis and other separation applications. I know all of you have heard about the issues we've been hearing about from the American West. The scale of the problem is making mainstream news now, but this is a problem that has actually been considered and been solved in the industry for a number of years. Reverse osmosis is globally the most prevalent form of water desalination, and it's also the most energy efficient form of water desalination. At the Tampa Bay desalination plant, for example, water is passed across cross-flow membranes, pass through the membranes. About 50% of the water that goes through comes out as fresh water and is then used for drinking water feeding into the municipal water supply. The scale of this plant is enormous. This plant uses 21 megawatts of electricity in order to power the high-pressure pumps to feed the water through 12,000 membranes. And so the capital and the energy costs of this plant is enormous. Desalination, however, is just not cheap. It is expensive because of thermodynamic limits. It's expensive because the energy of separation to separate materials has a limit and is expensive to produce. Reverse osmosis uses electricity as an energy input, whereas thermal desalination technologies use heat as an energy input, but are not as energy efficient. The majority of the operating cost is the high energy electricity used to pump these high pressure pumps, and the remainder really is in the capital construction of coastal water development in order to construct these plants. In theory, reverse osmosis uses about 1 kilowatt hour per meter cubed of water, fresh water produced. In practice, because our systems are not perfectly reversible, it's about 1.5 kilowatt hours per meter cubed. At Tampa Bay, we're looking more like 4 kilowatt hours per meter cubed, and part of the reason of that is the inherent limitations in the material properties of the membranes. The membranes have a tendency to foul, meaning that organic matter collects on the surface and reduces the performance of the membrane. But we're not able to pass cleaning chemicals through the membranes to reduce this fouling because the membranes degrade under drinking water levels of chlorine. This graph on the bottom left shows that exposing a polymer membrane to the levels of chlorine that you and I drink coming out of the tap actually degrades the membrane to the point where it's no longer desalinating water after 10 hours of exposure. And so we're looking at a problem where you have to chlorinate the water in order to clean it up so that you can pass it through the membranes, and then dechlorinate it in order to pass it through the membranes, in order to rechlorinate it to put it into municipal water supply. And so we're looking at membrane materials that can completely bypass this step in the desalination process. And I include cost competitive on this list for a particular reason. What we've learned a lot about the membrane industry is that bringing the cost of new technologies to current costs is extremely important. That better performance, it can perform better on 5 different metrics, but until it's cost competitive with the existing, until you can just replace it with the existing technology, it's not a wide adopter. And so bringing the cost down is extremely important. And in order to do that, we're looking at carbon-based materials, graphene as a material, but graphene's actually a very expensive material to produce. And so we're looking at a much more scalable feedstock, namely graphene oxide, which is derived from graphite, which we mine, which is dirt cheap to mine from the earth. Chemical exfoliation oxidizes the graphene sheets, pulls them apart into these nano sheets, which is known as graphene oxide, which looks a lot like graphene on the right-hand side, but actually is decorated with oxygen functional groups. Now, the electronics industry hates this material, loves this material because it's cheap, and hates this material because it's not as good of a conductor as graphene. And so we've taken a hint from the electronics industry and reduced the graphene such that we can remove some of those oxygen groups, which also removes some of the carbon lattice and creates defects. The electronics industry doesn't like those defects because, again, it reduces conductivity. But those defects, which we think from our computational studies that we can control reliably and scalably, are the pores that we're creating in our material. What we found when we look at these materials at very high resolution transmission electronic microscopy images is that the material behaves very differently under dirty and clean sample conditions. And so the clean sample is actually not what we see in day-to-day in our reverse osmosis plant membranes, but has a very different surface chemistry from the material that we've been studying so far. And so we actually were able to look at the surface chemistry and leverage that surface chemistry such that it improves the performance of the membrane across the board, from a resistance to chlorine, to stability in water, to resistance of biofouling, performance at high temperatures, and optimize those parameters, optimize that surface chemistry such that those parameters, those performance metrics are met. Moving to just finish up, I think one of the important takeaways that we've learned is that the performance benefits of reduced graphene oxide membranes actually extend beyond municipal desalination. And the reason for that is the phase space in terms of where membrane applications or membrane separation can actually be applied is a much larger space with graphene-based membranes. So with reduced graphene oxide membranes, we can operate membrane separation in harsher chemical environments, in very high or very low temperature environments. Polymer membranes have about a 10°C range that they like to operate in, which really limits a lot of applications, use of them in a lot of applications. And again, in high fouling feed sources, because as a much more chemically stable material, we're able to see much higher performance through fouling and through resistance to chemicals. So in conclusion, I want to thank everybody, Marin and Michelle and Leon from the Deshpande Center, the support, and also the extent of understanding of the industry that we've been able to get from this community as a whole. And so I have my poster next door. If you'd like to talk more, I would love to talk to you as well. Thank you very much.